Hello. We just have a few people here so far. Hi. Alrighty, we just have a few people here thus far. Okay, good. Hello, Alex. Hey, Hannah. Luai, Lorelai. Hello. Hope everybody's well. Hi, Claire. Hi, Sammy. Okay, we have 6. That's a little low, I think. I'm hoping people. Did somebody post? I know. Well, I put it in the WhatsApp group, didn't I? No, I put it on the thingamajigger. Okay. All righty. Well, we do have a few people here, so we can get started. As I hope people are still coming in. Hi, Rhea. I wanted to raise the question of what's going to happen in terms of the further. Here we go. More people are now logging on. I do not have any inside information. We've been working under the assumption that probably we will not have school after the spring break. That's not for sure certain. Hi, Justine. But we'll adjust accordingly once we know. The AP people will announce the dates on Friday for when the exam will be administered. So, hi, Samuel. Hi, Eric. Hi, Konstantin. Thanks for hanging out with us. So, at that point, we'll make a decision regarding the clausur, which is a little awkward because it's the day before spring break. Either way, we have 2 weeks of spring break, and I'm not. I think we're not having any mandatory sessions during spring break. Obviously, we're also not having any actual travel during spring break. Everybody's going to be at home. So I was thinking about the possibility of offering optional sessions during spring break, maybe twice a week. Right now, we've been meeting 4 times a week, which is our normal schedule, and that I'd switch to twice a week for people who want to still do some work. Okay, so twice a week is what I was thinking. Does that seem reasonable? Hannah said maybe that would be a good idea. So yeah, twice sounds good. I don't have. This is not. I'm not hurt either way. So unless I hear objections or yelling about, we definitely want more. I'm going to go with twice a week. Okay, I'll schedule twice a week, and we can see how that goes. And I'll obviously make it a convenient time, not too early, in order to make this work for you. And I'm happy. Yeah. Okay. Good. So I'll plan on doing twice a week during each week of spring break with you guys, and then we can get through one more test each week of the spring break. So we're doing 14 right now. Thursday, Friday, we're going to do 15. First week, we're going to go 16, and then we're going to go 17. Now, actually, I've assigned some of the other problems already from 18 and 19, and maybe even 17 already. So you also have those, but I think that's going to be good preparation. Again, I'm working under the assumption that probably after break, we'll move everything forward once they announce that we're not going back to school, which I think is going to happen, but I'm not sure yet. So we'll adjust that at that point. Okay, we are now close enough that we're going to get started in terms of talking about our physics problem that we have to deal with today. Our physics problem today is a circuit. If you printed it out, or you're looking at it on your screen or not, the clausura is scheduled right now for April 20th, the Monday after spring break. We will not have, it probably change. My gut is it's going to move forward 2 weeks. But again, we're not making that change until the AP announces and Berlin announces what's happening with schools. So here's the problem. It's a nice little circuit that you can see there. We have a power supply, DC power supply. We've got an ammeter, and here we go. Okay, that's our situation. I'll copy it over here for you guys. So we've got this is a DC power supply, and we've got a ammeter there. We've got R2 is 50 ohms. Let me come over this way. This is R1, which we do not know what it is. And down here, R3 is also equal to 50 ohms. That's our setup. Okay, that's our situation. And they say that they change the potential difference over here on the power supply, and they end up getting the following data. And I'm going to write it down here for a specific reason. We have delta V in volts, and then we have the current in milliamperes, and here's our table. We have 5 spots, 1, 2, 3, 4, 5. 2, 4, 6. Who do we appreciate? 8, 10. And then underneath it, we've got 40, 55, 97, 138, 155 milliamperes. Okay, it is showing up. There we go. Hi, Octave. So they're asking us in question A to draw, to plot current as a function of the potential difference. And I've prepared for you a little board that allows us to do that. Let's see. Yay! There you go. So we have a grid that we can use to plot these data points. And let's actually flip it upside down. There we go. And that allows us to put on here what we're labeling. So I'm going to use this as my origin down here. Makes it a little easier to label it, maybe. Yes. So this here is our x-axis. And this is our y-axis. And we're going to look at our values are on the x-axis. Remember, this is our x-axis, and this is our y-axis. Y-axis. Okay, so this is our y values. Whoopsie, doesn't really show up that. Okay, it's good, fine. Switch it back maybe a little bit. So there we go. Okay, so this is our Y, and this is our X. Let's take a look at our X values. Go up to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, that was brilliant. I should have started here. Not too late. I'm doing it anyway. So, okay, starting here. So this is our axis here. Ignoring what I'm doing there. Just ignore that. Shoot. Okay, so that allows us to go 2, 4, 6, 8, 10, and we're going to label it clearly V, delta V in volts. There you go. And we're going to take our vertical axis, and that's going to be the current in milliamperes. Largest value is 155. 1, 2, 3, 4, 5, 6 boxes here. So 2550, that would work. Yeah, barely, but that should work. So we're going to go here with 50 right here, 100 right there. Ah, shit, it's over here. There we go. And then over here is 150. That's pretty good. Ignore these marks here. Still working out how to use this grid, but that is better than what we did previously for the graphing situation. And the current, of course, is going to be plotted in milliamperes. So ready, set, go. Now, they don't actually say that, but of course, when we apply no current, there's no voltage, there's no current. Hi, Sachin. So let's take a look now. 2, 40, 2, 25, 50, 37 and a half, a little bit higher than that. So let's be like right there. Okay. There we go. Next one is 455, 450, 75, 1/5 along here. So maybe like right there. Okay. 697, just a little bit less than 100. So like right there. Good. And then we have 8, 138, 8, 100, 125, 137 and a half is right in the middle. There we go. And then last one is 10, 155, which is like right up there. There we go. Good. So there are our data points. We've plotted them nicely. We need a long ruler, and love to say that I'm prepared for that. That's pretty long, actually. I need some kind of long object that's going to work for that. Is this going to work? All right. Okay. Is this long enough? Picture frame. Actually not long enough. All right, here we go, broomstick. All right, so let's take a look. Put that there, put that there, put the line in, something like this. There we go. All right, that's pretty good, maybe a little bit low, but then again, I was using a broomstick, so sorry about that. Maybe a little higher would have been better, but it looks pretty good to me. Yeah, there we go. So let's see. When we do this kind of plot, remember, and we've talked about this several times, do not use data points. Use points on your line and make sure they're as far apart as possible, as reasonably possible. So obviously in this case, 0, 0 is a good choice, and we can circle it like that. And we can say 0, 0 is our first point. There we go. And then over here, we can choose a point that is maybe, for example, this one. And you do want to make sure it's taking at least one grid line. So in this case, that's right at 9 volts. 9 volts. And then in the y direction, 100, 125. That's at 137 or something like that. Okay. So 137 milliamperes is the y value. Okay. Graph good? Okay, good. So we've got our two values, and we can find the slope. Slope is equal to 137 milliamperes per 9 volts. And just a reminder, that's exactly what resistance is. Resistance is a measure of how many volts and how many milliamperes, are pushed through per volt. Other way around. How many volts are required? So this is the inverse, actually. So the slope is equal to 137 divided by 9. So resistance is specifically how many volts you need per ampere to push that amount of amperes through it. So the answer we get here, and we are going to put that in standard units. So it's 137 milliamperes, which is 0.137 amperes. So 0.137 divided by 9, we get 0.0152. 0.0152. We want to be hyper nerdy. We could add another digit. I think that's ridiculous. And that is amperes per volts. Okay. Making sure we're all okay with that so far. Okay, good. So we've got this value of 0.0152 amperes per volt. We can take our graph and place it over here. So slope equals 0.0152 amperes per volt. And that, of course, is equal to 1 divided by the total resistance of this setup. Okay, and that means that the resistance total is equal to 1 divided by 0.0152. Because we're Americans, we don't have to put the units there because we won World War II. Band of Brothers, really good series, by the way, if you're looking for something to watch. Okay, here we go. Taking that inverse is 65.7. That seems overly precise, but we can do that. 65.7 ohms is our calculated value for the total resistance. Okay, any questions? Nope? All good? Good. That was part A, and I already did part B as well. Take a picture of that. Good. And then we're going to move on. Okay, let's take a look. It's part C. So in part C now, we've got the graph, we've got the slope, we found the resistance. Now they're asking us for the value of R1. And oh, I should have probably left it here, but I'm going to redraw it quickly. No, I'm not. So C is asking, shit, I'm going to be able to redraw it. Okay, so we have the power supply. We had here this resistor, which is called R1. And over here, we have a 50 ohm right here. We have a 50 ohm right there. And then we come back over there. Correct. Okay, so C. Now we know that the total resistance is equal to, our value we found was 67 ohms. Okay, which is fine. 66 ohms. So we had 65.7 ohms was our measured value. Okay. All good. Now, we look at this circuit here, and the overall structure of this circuit, okay, the overall structure of the circuit, is it parallel P or is it series? Yes, I am serious. Parallel or series? Which one is it? Type it in the stream just to make sure you're still conscious and haven't passed out yet. Good. Yes. It is parallel with one element being series, and we are serious. Okay, so that means, of course, that for our parallel circuit, it is parallel, check it, we have two elements. We have the red element over here, okay, in parallel with our green element, which is this one, okay, which means that the total resistance, 1 over R total, is equal to 1 over R1 plus 1 over 100 ohms, because these two are in series. Okay, good. So let's take a look. 1 over R total we know, 1 over 100 we know. There are different ways of doing this, but I mean, let's be serious. You're not going to put this on, let's be serious, it's funny. Okay, so let's not put this on the same denominator. I mean, that's stupid, right? What's the lowest common denominator between 65.7 and 100? It's 6,570. Okay, that's stupid, right? Or something like that. Anyway, we're going to decimalize this. What that means is we're going to take the first number that we have there, okay? And we're going to take 1 divided by that, okay? We did that before, didn't we? So we had previously, and that's 0.01522. 0.01522. That's equal to 1 over R1 plus 0.01. And the nice thing about decimalizing this is that this is math that I can just do in my head. I know how to do this. I can subtract that from this. It's just going to take care of the 1. That's all that's going to happen, right? So we're going to get 1 over R1 is equal to 0.00522, 0.00522. Again, leaving the units off because of the whole World War II thing. Now, that means R1 is equal to 1 divided by that. Oh, missed a 0. Zero, 0.00522. And we use our calculator for that. And I get 191. Okay? Good. And that's part C. We're doing great. So I get 191 ohms. There we go. So let's take a look at the next question. Now, part D says, let's assume this is 12 volts. Okay. Good. 12 volts. And they're asking us to find the current through R2. So the current over here, R2. There we go. So obviously the current through R2 is, oh, that's actually cheesy easy. Oh God. Okay, that's so ridiculous. Okay, why are they asking that? I'm not sure. Okay, so let's take a look. Oh man, maybe this is difficult. Okay, maybe they're testing something that I should be thinking about testing. What's the voltage drop across R2? Delta V R2 is equal to what? How much voltage drops across resistor R2? Type it into the live chat. How many volts drop across resistor R2? Okay. 6 volts. 6 volts. Okay. Um, 6 volts is the correct answer. Was that not obvious? Honest feedback from the others. Or did everybody get it and it's easy? Easy or not? No feedback. Okay. Let's take a look here. I want to remind you about how we think about this in terms of our ski resort analogy. I think that's helpful. Okay. And specifically, in a ski resort analogy, the power source, thank you, Rhea, good, is the ski lift that lifts you to the top. So we're lifted from the bottom here to the top. So we're lifted 12 volts up, and then we come back down 12 volts, and we have a choice. We can come all the way through R1 and we drop 12 volts. That's a drop of 12. Or we can drop the 12 volts by passing through these two resistors along the red branch. When you go down the red branch, you go down the 50 ohm resistor first, the 50 ohm run, and then the second 50 ohm run. Because these two resistors have the same resistance, they must have, and the same current, they must have the same voltage drop. Okay, so it drops a certain amount here and it drops a certain amount there, and the total drop is 12 volts. Therefore, 6 volts drops here and then 6 volts drop there. Oh, yeah. Good. So that's why we got to keep practicing, Octave. Do that homework. Wink. Okay. Okay. So 6 volts drop here, 6 volts drop there. Total drop is 12 volts. So we have a 6 volt drop. And of course, if we know that drop is 6 volts, and then this is easy peasy because remember, the question asked how much current flows through R2. Okay. How much current flows through R2? Well, easy peasy for that one too, because Ohm's law. Okay, I'm not even going to write it down. If the voltage is 6 volts that drops across the 50 ohm resistor, how much current flows there? Find the current flowing through the 6 ohm resistor. Ooh, this is a really professional rig I got here. Okay, so how much current flows there? Type it into the chat. Go. Okay, good. 120 milliamp. Now, that's one way of looking at it, and we got the correct answer. However, as Octave pointed out, well, I'm not sure I'm going to see that. Well, if you're not seeing that, there's another way of looking at it. You can say, okay, well, the current that flows through R2 is the current that flows through both resistors over here. Both these resistors have that same current. This branch has that same current. Well, that means 100 ohms right here, right? The 100 ohms over there. This is for the right or the red branch, right? Those 12 volts press current through 100 ohms. Okay, well, that's the same thing. That's 0.12 amps. Of course it is. Got to work out. I mean, it doesn't make sense if it doesn't. I mean, current that flows through here flows through there as well. Okay, so that's another way of looking at it. So you can use it, use the whole red branch or just looking at R2. Either approach works. Okay, so let's take a picture of that and let's move on to part E and then F. I'm going to leave this here now. Okay, there's our circuit, and we're going to modify the circuit by taking this resistor down here, removing it, and putting in a switch and a capacitor. Okay, and we have a capacitance of 4 nanofarads here. This is a capacitor over here. We've got a resistor R2 with 50 ohms there, and R1, of course, we had at 66 ohms. Yep. So this one here is now labeled at 66. There we go. That's our circuit. Good. Let's see the question they're asking us. They've got the capacitor in there, and they're asking, immediately after I close that switch, how much current is there through resistor R2? This is R2 up here. R2 is this, and this is R1 here. Okay, so when we just have closed the switch, this capacitor has no charge. How much resistance does an empty capacitor have? Resistance of an empty capacitor is effectively how much? Type it in the stream. Okay, the resistance of an empty capacitor with no charge is how much? You guys still there? Oh, 0. Good. Thanks, Rhea. So yes, it is 0. An empty capacitor has no resistance. Okay, so this capacitor has no resistance. So no resistance means delta V across a capacitor is how much? How much voltage drop is there? How much potential drops? Whoa, 191? Oh shit, our total was 66 and this was 191. Thank you. Good. Good, thank you. So the empty capacitor has no resistance. Therefore, how much voltage drops across an empty capacitor? Awesome, that's wrong. Okay, so the voltage drop for a capacitor is always proportional to the charge. If there's no charge on that empty capacitor, that means there's zero voltage drop across the capacitor. Correct. The whole branch still drops 12 volts, but the capacitor has no drop. If the capacitor has 0 and the total red branch has 12 volts, internet has been bugging out. Okay, so the red branch over here has a total drop of 12. Capacitor is 0. Therefore, what's the drop across R2? Okay, maybe, I'm not sure if it's on my end or not. So whole branch still drops 12. I'll just answer my own question. 12, good. It's 12 volts, good. So if R2, there's a drop of 12 volts across there, that means, of course, that the current flowing through R2 is the voltage drop across R2 divided by the resistance R2, okay? All right, Ohm's law, 12 volts divided by 50 ohms is equal to 0.024. Wait, times 5 times, no, it's 0.24, sorry. There we go. 0.24 amps. Okay, 0.24 amps or 240 milliamps is another way of putting the same answer. Okay, good. That's E1. Let's get to part E2, not part EII. There we go. Part E2 asks, a long time after the switch is closed, will the magnitude of the current in R2 be greater than, less than, or equal to the current through R2 found in part D? Well, that's a ridiculous question. Sorry, that's so easy. That's really very, I'm sorry. Now that could be intimidating. So after a long time, that means the capacitor is now full, okay? And just a reminder, the resistance of a full capacitor, and full capacitor always means it has as much charge as can be put on there with the potential available for it, potential difference. So full capacitor has infinite resistance. That means the red circuit has no current. And of course, no current, zero current, is less than whatever current we had previously. So less than. Okay? And I just spoke the answer. I mean, that's silly. A full capacitor, a long time later, has effectively infinite resistance. No current will flow through that branch. Therefore, it has zero current flowing through R2, and that's, of course, less than what it was before because it was not zero. Good. Now, coming to part F. Wow, they're not even doing any kind of like time-dependent stuff. It's a little bit disappointing. This is a little bit too easy, I think. The 4 nanofarad capacitor is replaced with an uncharged 10 nanofarad capacitor. Will the magnitude of the current in R2 immediately after the switch is closed be greater than, less than, or equal to the current in part E1? Hello. What is it? So we switch the 4 nanofarad to a 12 nanofarad. So what happens to the current immediately after closing the switch? It's still the same, exactly. Of course, because what we just did is the same idea. When we close the switch, the empty capacitor has no resistance, whether it's 4 nanofarads, 12 nanofarads, 17 picofarads, 0.3 farads, doesn't matter. It has zero resistance. Yeah, it has no charge, exactly. Oh yeah, I think this should be a slam dunk. It's hate to say it, it's not really an AP Physics C question, is it? Because where's the calculus? I mean, I was expecting something here with some kind of time dependence, or at least a graph, or something. It's a little bit easy, but if you get it, that'd be awesome. I think you guys would definitely rock this thing. I would hope. And that brings us to the end of the question. Did they ask us for a justification? They did. I mean, we just did the justification. I think that's pretty reasonable. Okay, so that brings us to the end of this problem. We have just a few minutes left. If you are viewing this later, we did agree, or if you missed earlier, we did talk about the next 2 weeks. I will do one session, 2 sessions per week for people who still want to review. That'll be obviously optional, completely optional, and we'll see how many people show up. The College Board will continue to post stuff in terms of having those happen. For their review sessions. There are 2 review sessions today that are relevant for mechanics. I posted those. There's one at 17 o'clock our time, 17 Uhr, and there's one 18 Uhr. Both of those look good. Let me know how they go. I do think live can be more fun than taped, but then again, if your internet's glitchy, then it's difficult. So if somebody wants to watch those, take a look. Otherwise, we're getting to the end of our time. In terms of suggestions for when we should meet in the next couple of weeks, are there preferences in terms of what days would be best? Like Monday, Thursday, Tuesday, Thursday, Tuesday, Friday. What are the better days for you guys if we're going to have 2 sessions a week that are optional, or are there no opinions because most people are like, I'm not going to show up anyway. So. Okay. All right. Well, we can talk about it. Maybe you guys can. Maybe I'll put a post on. Oh, okay. I will put a post on Google Classroom, and then you guys can weigh in. The people who are interested and say, "Oh, okay, these days would be better. Tuesday, Thursday, maybe." Okay. 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 Sammy likes. Okay, that as well. All right. Okay. All right. Thanks for coming by. I hope you enjoyed and learned something. And I'll see you guys on Thursday, per usual. And specifically, that means, oh yeah, Thursday, 10:37 to 11:22. Thursday is food day. Thank you, Justine, for organizing that. And show up with your snacks and food, and wait. I'm waiting. Right. The clausur will have only FRQs. That's correct. The exam has only FRQs. We will also only have FRQs. That's the plan. Correct. Probably. I don't know. I think I am planning on giving you FRQs for the clausur to make it a practice for the exam. The AP exam has only FRQs. My plan is to also do that for the test, the clausur. Okay? All righty, we're at 12:14 and almost over. Have a good lunch. See you guys Thursday. Bye-bye.